Okay, let's unpack this. While the results of AI models often seem like pure magic, just appearing out of nowhere.
Yeah, like computation just poof, creates intelligence.
Exactly. But the truth behind the curtain is that their power really comes from some incredibly detailed fundamental processes,
Yeah.
a whole lot of meticulous work.
Absolutely. The real magic, if you want to call it that, is in actually building those powerful models from the ground up. And that's what this deep dive is all about, based on the sources you've given us.
Right.
You've got a fantastic stack here, guides, blog posts, covering everything from the basics like data labeling
The real foundational stuff.
to specific models you hear about constantly, like LLMs, diffusion models. And it covers how training works, plus this really great real-world example of scaling up human data labeling.
So our mission here really is to cut through the complexity in these guides. We want to highlight the most important concepts, pull out those practical insights, and maybe uncover some, surprising details, all tailored just for you.
Think of it as us exploring these interconnected ideas together, using these sources as our map. We'll start with foundations, get a handle on the models everyone's talking about, touch on how they learn, and then look at the real challenges of making it all work at scale.
Okay, so let's jump right into that foundation, data labeling. What exactly is it based on these sources, and why is it so heavily emphasized?
Data labeling is, well, it's truly the bedrock for so much of modern AI,
Yeah.
especially supervised learning. Fundamentally, it's the process of assigning context or meaning to raw data.
Like pictures, text, sound.
Right. Images, text, audio, video,
Mm-hmm.
giving it structure. So the
Yes.
machine learning algorithms actually have something understandable to learn from.
It's like giving the machine flashcards with the right answers already filled in. And the sources really hammer home its importance, mentioning this shift towards data-centric AI. What's that about?
That's a really key concept they bring up. It signifies this move where the focus isn't just on tweaking the model or the algorithm itself.
Which used to be the main focus, right?
It often was. But now there's increasing emphasis on improving the data, its quality, its quantity, and crucially, the labels. The idea is even the smartest model can't learn effectively from bad data.
Which brings us right back to that classic computer science idea. Garbage in, garbage out.
Precisely. Applied directly to ML. If your data, or more specifically the labels you put on it, are poor quality, inconsistent, maybe biased.
Then the model trained on it will be too.
Exactly. It'll produce unreliable, poor, or biased results. High-quality data, high-quality labels, they're just non-negotiable according to these sources.
Okay, so that's the why. How do teams actually get this data labeled, especially at scale? The sources talk about different ways to build the workforce.
Yeah, you generally see a few main approaches. On one end, there's automated data labeling.
Using AI to label data for AI?
Sort of, yes. It's great for efficiency and handling huge data sets if the task is relatively simple or the data is consistent. But the challenge, as the sources point out, is managing the errors.
Right, trusting the automation, especially with edge cases.
Exactly, those tricky examples the automation hasn't seen before. Then you have the other end, human-only labeling.
People doing the work.
Right, humans are fantastic for complex, subjective tasks. Think understanding nuance in language or detailed image annotation, you get high quality. But it's slower, naturally, it's more expensive, and keeping lots of different people labeling things consistently, that can be a real challenge. Subjectivity creeps in.
Which leads to the third way, which seems to be the most common.
Yeah, the sources definitely lean into human in the loop, or HITL. It's often presented as the best of both worlds.
How does that work in practice?
You use automation for maybe the first pass, the easier stuff, or initial suggestions. Then humans come in to review, correct, handle the complex edge cases, or provide feedback. It's about augmenting the machine with human smarts.
Okay, that makes sense. So where do these humans come from? The materials outline a few sourcing options.
You've got a few choices. You could build your own in-house team. That gives you maximum control, deep domain expertise.
But it's expensive? Lots of overhead.
Right. Then there's crowdsourcing. You get access to a huge, flexible pool of people quickly. But the sources do warn about potential quality risks.
Yeah, and maybe not getting that specific domain knowledge you need for certain tasks.
That's a key point they raise. The third option discussed is partnering with specialized third-party data labeling providers.
What are the advantages there, according to the sources?
Well, these partners often bring established technical expertise, optimized workflows, and the ability to scale up or down efficiently. They might have better tooling and training, leading to higher quality.
The trade-off being?
You give up some direct control. And you really need to trust your partner, especially if you're dealing with sensitive data. That's where things like SOC2 or SOP certifications, which the sources mentioned, become really important.
Got it. So you have the people or the process. What about the tools? The sources touch on different data labeling platforms too.
Yep. There are open source tools available, great for getting started, maybe for specific niche needs, but they might lack scalability or the latest features.
Or you build your own.
You can build in-house tools. Complete customization, but it's a significant development and ongoing maintenance effort. Can be very costly.
And the third category.
Commercial platforms. These are often highlighted because they offer robust tooling, dedicated support, sometimes access to trained workforces, and they tend to incorporate state-of-the-art features driven by serving lots of different clients.
Okay, so regardless of the workforce model or the platform you use, the absolute key takeaway, stressed repeatedly in these sources, is maximizing label quality.
Absolutely critical. And they introduce some key metrics to measure this.
Like precision and recall, those come up a lot. Can you break those down simply?
Sure, think of precision this way. Of all the times the model said, yes, this is X, like this image contains a cat, how many times was it actually right? High precision means fewer false alarms, fewer false positives.
Okay. And recall?
Recall asks, of all the actual X's that were really there, all the real cats in the data set, how many did the model correctly find? High recall means fewer misses, fewer false negatives.
Right. And they often conflict, don't they? Trying to get one higher might lower the other.
Exactly. There's an inherent trade-off, often visualized by the precision recall curve. Where you want to be on that curve depends entirely on your specific application. Is it worse to miss a real cat? You need high recall. Or to mistake a dog for a cat? You need high precision. The sources emphasize you have to decide which error is more costly for your use case.
That makes sense. So quality is king. What are some of the best practices the sources suggest for actually getting those high-quality labels? They list quite a few, maybe highlight a couple of key ones.
Okay, let's pull out a few impactful ones. One that sounds simple but is crucial, providing incredibly clear and comprehensive instructions to the labelers.
Ambiguity is the enemy.
Totally. If different labelers interpret the task differently because the instructions are vague, your data quality is going to suffer right from the start.
So it's not always the labeler's fault if things are inconsistent. Could be the instructions.
Exactly. Another really important practice they highlight is using benchmark tasks, sometimes called a golden data set.
How does that work?
You get a small group of highly trusted experts, maybe your internal team, to label a subset of the data first. These become your known, correct answers, the gold standard. Then you mix these benchmark tasks into the regular workflow for the broader labeling team.
Ah, like little pop quizzes to check their work in real time.
Kind of, yeah. You monitor their performance on these known tasks to evaluate their quality, screen out poor performers, and ensure consistency during the labeling process, not just finding out about problems at the end.
That's smart. What else stood out?
Related to that is inspecting common answers. If you see many different labelers making the same mistake on the same piece of data,
It's probably not just random error.
right, it's a strong signal that maybe the instructions are confusing for that specific case, or the data itself is ambiguous, or maybe even your benchmark answer is wrong. You use that feedback to improve the process, update instructions, clarify edge cases, refine the benchmark.
So it encourages continuous improvement of the whole system, not just blaming individuals.
Exactly. And one last really practical one, create calibration batches. Before you launch a massive labeling project on millions of items, do a small pilot run first.
Test the waters.
Precisely. Label a small batch, review the quality very carefully, identify any issues, fix your instructions or process, then scale up. Don't just jump in blind.
These practices really show how much thought and, frankly, engineering goes into what sounds like a simple task. So, okay, we have this high-quality labeled data foundation. Where do the sources say, this takes us next?
Well, with that foundation, you can start training powerful models for specific tasks. The sources focus heavily on two major areas, computer vision and natural language processing, or NLP.
Let's start with computer vision teaching machines to see what kinds of labels are needed there.
The sources detail quite a variety, depending on the visual task. We don't need to list every single one, but some common ones are illustrative.
Like bounding boxes.
Yeah, probably the most fundamental, just drawing simple rectangles around objects. Super useful for detecting and locating things. Cars for autonomous driving, products on a shelf, that sort of thing.
But sometimes a box isn't precise enough, right?
Exactly. That's where polygons come in. You trace the exact outline of more complex, irregular shapes. Think buildings, trees, lakes in satellite images, maybe damaged areas on a car panel.
Okay. And then there's segmentation, which sounds even more detailed.
It is. Segmentation involves labeling at the pixel level. There are a few types mentioned. Semantic segmentation assigns a class label to every single pixel in the image, like this pixel is road, this pixel is sky, this pixel is building.
So categorizing everything.
Right. Then there's instance segmentation, which goes a step further. It labels pixels belonging to each individual object within a class. So not just car, but car number 1, car number 2, tree number 1, and so on.
Ah, so semantic is what category, and instance is which specific one.
You got it. And the sources also mention panoptic segmentation, which is basically a combination of both. It assigns both a class label, like car, and an instance ID, like car3, to every pixel. This gives a really rich, comprehensive understanding of the entire scene.
Wow. You can see how that would be critical for, say, a robot navigating a complex environment, or for detailed medical image analysis.
Absolutely. The required precision drives the annotation type.
And what about video? That adds the dimension of time.
It does. Video annotation is more complex because you have to consider how objects and labels change across frames. The sources highlight the need for tools and techniques that manage this temporal aspect, things like linking the same object with a unique ID even if it goes off screen and comes back.
Makes sense. And multimodal data, mixing images with audio or text.
Yeah, that's increasingly important for applications trying to mimic fuller human perception. Think AR/VR, understanding the visual scene and the sounds within it, or analyzing sentiment from both facial expressions in video and tone of voice in audio. The challenge, the sources note, is keeping annotations consistent across these different data types.
Interesting. The sources also briefly brought up synthetic data, generating data instead of collecting real-world stuff. Why do that?
Synthetic data generation is useful in a few scenarios. Maybe real data is really hard, expensive, or even dangerous to collect, like those rare specific edge cases for self-driving cars, like a very unusual type of
You
accident.
can't just wait around for those to happen.
Right. Or you might use it to deliberately create more balanced data sets
Hmm.
to try and mitigate bias found in real-world data.
Hmm.
The sources add an interesting caveat here, though. While synthetic data itself comes with perfect computer-generated labels, if you mix it with real-world labeled data, the accuracy of your real data labels becomes the bottleneck. If your real labels are noisy or inaccurate, they'll still degrade the model's performance, even if half your training data was perfectly labeled synthetic data.
Huh. That's a really practical point. Quality of the real data still matters immensely. Okay, let's shift gears from seeing to understanding natural language processing, NLP. How does labeling work there?
So NLP is all about teaching machines to process and understand human language. Labeling provides the necessary structure. Common types mentioned in the sources include things like part-of-speech tagging.
Identifying nouns, verbs, adjectives.
Exactly. That helps models grasp the grammatical structure of sentences, which is fundamental for things like chatbots or virtual assistants understanding queries.
And named entity recognition, or NER.
Right, NER is about identifying and classifying key chunks of text into predefined categories like person, organization, location, date. Super important for extracting information, building knowledge graphs, analyzing customer feedback to see who or what they're talking about.
What else?
Text classification is another big one. Categorizing entire pieces of text, think classifying emails as spam or not spam, analyzing the sentiment of product reviews, positive, negative, neutral, or routing customer support tickets based on topic. And for audio data, the first step is usually transcription, converting speech to text. That text then becomes the data you can apply other NLP labeling techniques to.
Okay, and this naturally leads us to the topic that's been everywhere lately, large language models, or LLMs.
Indeed. The sources define these as, well, massive machine learning models trained on absolutely vast amounts of text data. They can understand, classify, summarize, translate, and even generate remarkably human-like text.
We're talking about the famous ones like GPT-3, GPT-4, Google's PaLM2, Anthropic's Claude.
Those are the big names. And fundamentally, as the sources explain, they work as incredibly sophisticated language prediction models. Given a sequence of words, or tokens as they're called.
Tokens are like pieces of words.
Often, yeah. Subwords of words. Given a sequence of tokens, the LLM predicts the most statistically likely next token based on the immense patterns it learned during training.
And their impact on NLP has been, well, revolutionary, hasn't it?
Absolutely. They've suddenly made advanced capabilities much more accessible. Things like writing decent first drafts of emails or articles quickly, helping programmers code more efficiently or debug, summarizing long documents instantly.
Making chatbots actually feel useful for a change.
That too. And the sources note they're increasingly available via APIs or even as open source models, which has fueled innovation.
And led to new jobs, like the prompt engineer.
Right, but here's a really crucial insight the sources emphasize. Despite being trained on, huge swaths of the internet, these base LLMs are generally not great specialists right out of the box.
The jack of all trades, master of none issue.
Kind of, yeah. They have broad knowledge, but lack deep expertise in specific domains or tasks. To really unlock their value, especially for specific business needs, the sources say you need to fine-tune them.
Fine-tuning. What does that involve?
It means taking a pre-trained base LLM and continuing its training, but on a much smaller, carefully curated data set that's highly relevant to your specific task or domain.
So if I'm a bank, I'd fine-tune it on financial reports and analysis.
Exactly. Or an e-commerce company might fine-tune it on product descriptions and customer reviews. That targeted data teaches the model the specific nuances, terminology, and style needed for that use case.
So proprietary data and targeted labeling come right back into the picture, even with these giant models.
They're absolutely crucial for tailoring the capabilities. And the sources list a huge range of common LLM use cases that are enabled either by the base model or, more often, by fine-tuning.
Like what? Give us a few examples.
Sure. Classification and content moderation, think sentiment analysis of customer feedback, automatically routing support calls, organizing user reviews, or flagging harmful content online.
Okay.
Text generation, obviously creating human-like text for answering questions, drafting social media posts, even mimicking specific writing styles. Text extraction, pulling key information out of unstructured documents, like summarizing call center transcripts or finding specific clauses in contracts.
The summarization itself is a big one, too.
Definitely. Creating concise summaries of long reports, news articles, multiple data sources, sometimes combining extraction with summarization and even citing sources.
What else?
Question at. Answering over specific knowledge bases like an internal company wiki, enhancing search engines, both public and within enterprises. Software programming assistance tools like GitHub Copilot are powered by LLMs, and just acting as general assistants for tasks like data analysis, content brainstorming, even helping with product design ideas.
It really sounds like they're becoming incredibly versatile tools across pretty much every industry.
They are. Insurance, retail, finance, the sources give specific examples. It's helpful to quickly look at where they came from, too.
Yeah.
The sources provide a neat little history.
Right. NLT isn't brand new.
Not at all. Early ideas go way back,
Yeah.
but modern neural network approaches kicked off with things like recurrent neural networks, RNNs, in the 80s, and then long short-term memory networks, LSTMs, in the late 90s, which were big for handling sequences like speech.
But the major leap forward came more recently with the transformer architecture in 2017. The attention is all you need paper.
That was the game changer. The attention mechanism let models weigh the importance of different words in a sentence, regardless of how far apart they were. And crucially, it allowed for massive parallelization during training.
Which let them scale up massively.
Exactly. That paved the way for models like Google's BERT in 2018, which was really good at understanding context for classification tasks, and then OpenAI's GPT series, which focused more on generation.
And then we saw that explosion in model-sized GPT-2, GPT-3, Google's PaLM, going from millions to hundreds of billions of parameters.
Yes, for a while, bigger seemed unequivocally better. More parameters often meant more capabilities. However, the sources point out a more recent trend, maybe a plateau effect.
Oh, simply making models bigger isn't the only answer anymore.
It seems the returns are diminishing. Just adding more parameters isn't yielding the same leaps in performance, so the focus has shifted.
Shifted to what? This is interesting.
The emphasis now, according to these sources, is much more on the quality of the pre-training data and, critically, on post-training techniques. Things like supervised fine-tuning, SFT, where you explicitly train the model on examples of desired behavior, and reinforcement learning from human feedback, RLHF. Plus, the whole art and science of prompt engineering.
And these techniques can make smaller models perform better.
Sometimes dramatically so. The classic example mentioned is InstructGPT. It was a 1.3 billion parameter model, but because it was trained using human feedback, RLHF, humans actually preferred its outputs over the much, much larger 175 billion parameter-based GPT-3 model.
Wow. That really highlights how important that human element in targeted training is, not just raw scale.
It absolutely does.
So let's dig into those techniques a bit more. Reinforcement learning from human feedback, RLHF, what is that exactly?
RLHF is a way to train models by directly incorporating human preferences into the learning process. Instead of just predicting the next word based on probability, the model learns to generate outputs that humans explicitly rate as being better.
Better in what sense?
More helpful, more honest, less harmful, better at following instructions, basically, more aligned with what the user actually wants. Humans rank different potential outputs from the model, and that ranking data is used to train a reward model, which then guides the LLM during further training.
So humans become active trainers, shaping the model's behavior directly through feedback.
Exactly. It's why models like InstructGPT, and especially ChatGPT, which heavily used RLHF according to the sources, feel much more conversational, helpful, and less prone to generating nonsense or harmful content compared to earlier base models. It makes them safer and more useful for real-world interaction.
Makes sense. And prompt engineering. We hear that term a lot now.
Yes, it's become a really critical skill. It's essentially the practice of carefully designing the input text, the prompt that you give to the LLM, in order to guide it towards producing the specific kind of output you want.
It's not just asking a question, it's crafting the right question or instruction.
Precisely. A good prompt engineer understands the LLM's capabilities and limitations, figures out the desired output format and content, and then uses specific words, phrasing, examples, or context within the prompt to steer the model effectively.
The sources gave some examples of techniques, like setting default instructions.
Right. Using system prompts or default instructions. You can tell the model up front how it should behave generally. Like, you are a helpful financial assistant for Acme Corp. Never give advice outside of finance. Be polite and concise. This helps enforce brand voice, company policies, or desired persona consistently.
What about getting structured data out?
That's another key technique. Specifying output templates. Instead of just letting the model ramble, you can instruct it, for example, extract the company name, revenue, and date from the following text, and output it as a JSON object with keys, company, revenue, date. This is crucial for integrating LLM outputs into downstream processes.
And they also mentioned adversarial prompting, trying to trick the model.
Yes, that falls under the umbrella of red teaming. You deliberately craft prompts designed to elicit disallowed outputs, or to see if you can confuse the model or make it contradict its safety guidelines. Things like role-playing scenarios, using weird formats, trying to inject new instructions mid-conversation.
Why do that?
To find the model's weaknesses and vulnerabilities before they're exploited maliciously. It's a crucial part of testing and improving the model's robustness and alignment. The sources note it's a whole field in itself.
Okay, that's a fantastic overview of LLMs and how they're being refined beyond just size, with data quality and human input playing such key roles. Let's maybe zoom out again and touch on the general process of training ML models applying to more than just LLMs.
Sounds good. So at a really high level, machine learning models learn patterns from data without needing explicit programming for every single rule. They usually consist of layers of interconnected nodes, often called neurons, and the connections have weights.
And training is about adjusting those weights.
Exactly. During training, the model processes the input data, makes predictions, compares them to the known correct labels in supervised learning, and calculates an error or loss. It then uses algorithms like backpropagation to adjust the weights in a way that minimizes this loss over many iterations or epochs.
The goal being convergence, where the loss stops decreasing significantly.
All right, the model's performance stabilizes. ML engineers guide this whole process by choosing the data, the model architecture, tuning various hyperparameters that control the learning process. A key goal, though, isn't just to minimize loss on the training data,
but to ensure the model generalizes, performs accurately on new data it's never seen before.
Absolutely crucial. And to measure that and to prevent the model from just memorizing the training data, which is called overfitting, you have to split your data set.
Right. Into the training set, validation set, and test set.
Correct. The training set is the bulk of the data, maybe 50–90%, used for the actual learning, adjusting the weights. The validation set, say 5–20%, is used during the training process to tune those hyperparameters like learning rate, number of layers, and to make decisions like when to stop training to prevent overfitting, known as early stopping.
And the test set.
The test or holdout set, another 5–20%, is kept completely separate. It's only used once at the very end, after all training and tuning is done, to get a final, unbiased estimate of how well the model performs on truly unseen data. It's the final exam.
Got it. And models can be trained on all sorts of data, as the sources mentioned, not just images and text.
Right. Tabular data, your classic spreadsheets with rows and columns, is very common, often needing feature engineering. Audio signals, 3D point clouds from sensors like LiDAR, and, as we discussed, increasingly multimodal data combining different types.
And the types of models themselves have evolved significantly too.
Definitely, from simpler models like support vector machines, SVMs, or basic feed-forward networks, to models designed for sequences like RNNs and LSTMs, then convolutional neural networks, CNNs, which revolutionize image processing
Leveraging GPUs effectively.
hugely. And reinforcement learning approaches like Q-learning, techniques like Word2Vec for text embeddings, and now the transformer architecture, which is dominant not just in NLP, but increasingly influencing vision models too.
The sources list some specific well-known models like AlexNet, YOLO, UNet, GPT-3, Stable Diffusion, showing how these architectures get applied.
Yeah, those are practical examples of these concepts in action.
Okay, so when you evaluate the final trained model on the test set, what metrics do you look at? We talked about minimizing loss during training.
Right, loss is what the model optimizes internally. But for evaluation, accuracy is common, simply the percentage of correct predictions. Useful, but can be misleading if your classes are imbalanced.
Like if 99% of data is Class a model predicting Class A always gets 99% accuracy but is useless.
Exactly. That's where precision and recall, which we discussed in the labeling context, are vital for understanding model performance on specific classes. And the F score, often the F1 score.
The balance between precision and recall.
Right. It's the harmonic mean of the two. It gives you a single number that balances both, which is really important in situations where both false positives and false negatives are costly, like in medical diagnosis or safety systems.
Finally, the sources just touch on some practical realities of training.
Yeah, things like training can take a long time, from hours to weeks or even months for huge models. Model size directly impacts memory and compute needs. You need a decent amount of data. The sources mentioned needing maybe 1,000 examples as a rough minimum to start avoiding severe overfitting, but often much more is needed. And large-scale training usually requires powerful hardware like GPUs or TPUs, often distributed across many machines.
It's a resource-intensive process.
It really is.
Okay, this is great context. Let's try and connect all this back to the real-world challenges with that case study from the sources. Labeling 1 million data points per week for OpenAI's early work on GPT-2.
Yeah, this is where the rubber really meets the road. OpenAI needed human preference data to fine-tune an early GPT-2 model, essentially applying the core idea that later became formalized as RLHF, though the source predates that specific term.
And the challenge was the speed and scale.
Extreme speed and scale. They needed labels back in under 30 minutes, incredibly low latency, and had to handle a throughput of about 5,000 labels per hour. This was for online labeling.
Meaning the model was generating outputs, humans rated them almost immediately.
And that feedback was fed back quickly to retrain or update the model. Cycle time was critical.
But the task itself was subjective, right? Picking the most descriptive text continuation.
Exactly. That subjectivity made it really hard to ensure quality and, crucially, to distinguish labelers who were genuinely trying their best from those who might just be guessing to meet speed targets.
So how could they maintain quality under that kind of pressure? The source says traditional methods wouldn't work.
Right. Things like having multiple people label the same item, redundancy takes too long. Calculating quality metrics usually involves looking back over time, which also breaks the 30-minute latency requirement.
So what was their solution, according to the source?
Their core innovation was the sophisticated use of benchmark tasks, building on that golden dataset idea we talked about.
How did they implement it for this speed?
They had a small group of highly trusted internal researchers label a subset of tasks first, establishing the high-confidence ground truth. These known benchmark tasks were then secretly mixed into the high-volume task stream given to the larger external workforce.
Ah, so the external labelers didn't know when they were being tested.
Precisely. Their performance on these hidden benchmarks served as a real-time filter for quality. If a labeler consistently failed the benchmarks, they could be flagged or removed quickly. It was a way to leverage the high trust in a small group to validate the quality of a much larger, faster workforce, enabling both scale and speed with some quality control.
That's clever, but the source mentioned it wasn't a perfect system right away. They had to iterate.
Oh yeah, absolutely. Real-world systems always need refinement. One issue they encountered was labelers developing heuristics or shortcuts.
Like figuring out a pattern.
Exactly. In the descriptiveness task, they noticed labelers might start just picking the longest text option, because often that was the most descriptive one. But that's not always true, and it bypasses genuine judgment.
So how did they fix that bias?
They specifically created anti-bias benchmark examples tasks, where the longest option was deliberately not the correct answer, and they weighted these examples more heavily in the quality scoring. They essentially had to teach the benchmark system, and thus the labelers, not to rely on that simple heuristic.
That's fascinating, actively fighting the shortcuts. What else?
They also implemented dynamic serving of benchmarks. If the system suspected a particular labeler's quality might be dipping based on recent performance, it could automatically increase the percentage of benchmark tasks sent to them for closer monitoring.
Wow, real-time adaptation.
And they stressed the importance of testing and monitoring everything. They used synthetic projects, basically sandbox copies of the live labeling task, to safely test changes to instructions or workflows quickly. Plus, robust monitoring dashboards, tracking agreement rates, throughput, time for task with alerts, and crucially, daily qualitative audits by their internal team comparing samples against expert labels.
This case study really drives home the practical engineering and ingenuity needed to get high-quality data at scale, especially under tough constraints like speed and subjectivity. It ties everything together.
It really does. It shows that building these advanced AI systems isn't just about the algorithms. It's deeply about the data pipeline
Yep.
and the human processes wrapped around it.
Incredible. We've covered a huge amount of ground here. We started right at the beginning with the absolute necessity of high-quality data labeling and this idea of data-centric AI.
Yeah, the foundation.
Then we saw how that labeled data fuels applications in computer vision and natural language processing. We dove deep into large language models, what they are, their rapid evolution.
And importantly, how techniques like fine-tuning, reinforcement, learning from human feedback, and prompt engineering are now key to making them truly useful and aligned, maybe even more so than just raw size.
Right. We also touched on the general mechanics of training any ML model splitting data, the goal of generalization, different model types, and metrics.
And wrapped it up with that fantastic OpenAI case study, showing the real-world complexities and solutions for scaling human data labeling under pressure.
The big picture takeaway from all these sources seems crystal clear. Powerful AI doesn't just happen. It's built on deliberate, often really complex processes of preparing data, training models meticulously, and constantly refining them.
And that garbage in, garbage out principle, it echoes through everything. Data quality is just fundamental.
And what's also striking is how central the human element remains throughout this whole pipeline, from creating the initial labels to providing the preference feedback that shapes model behavior in RLHF.
To crafting the prompts that guide the final output. The tools are getting more sophisticated HITL systems, prompt engineering frameworks, but they're all fundamentally about leveraging human understanding more effectively.
These insights really do flow directly from the detailed guides and practical experiences you brought for us to explore in this deep dive.
It definitely makes you think about how the relationship between people and AI is evolving, doesn't it?
It really does.
Yeah.
Which leads to a final thought, maybe something for you, our listener, to ponder. Given this increasing reliance on high-quality data curation, on human feedback for alignment, on careful prompt engineering, what does the future really hold for the human role in developing AI? Are we moving away from being programmers who define explicit logic?
And becoming more like expert gardeners or guides for these powerful models, cultivating the data, providing the feedback, steering them towards desired outcomes.
It's a fascinating question to consider as these technologies keep moving so fast.
Indeed.
Well, thank you so much for bringing this incredible set of sources for us to dive into today. It's been genuinely insightful exploring them with you.
And we really hope this conversation helps you, our listener, reflect on these key ideas about data, models, training, and the human role, all drawn from the materials provided.
Maybe it sparks some ideas for your own further exploration. You could dive deeper into specific model architectures we mentioned, or look into the engineering challenges of deploying these systems reliably, or even consider the economic shifts happening as these AI capabilities become more widespread.
Lots to think about. Thanks for joining us for this deep dive.